In this lesson, we will examine the various types of controllers used by pressurization systems. We will look at the required pilot inputs and at the indicating systems used to inform the crew of correct system operation. We will look at a typical flight profile using an automatic pressure controller, and finally, we will see how the pilot can control the pressurization manually. Pressurization controllers vary in construction and operation. On simpler small aircraft, they may be purely pneumatic in their operation. On old generation jets, they are electro-pneumatic, and in the case of most modern aircraft, they are electronically operated. Whatever type of controller is used, it will receive signals informing it of both the cabin and ambient pressures. The controller has three functions. It will control the cabin altitude, it will control the cabin altitude rate of change, and it would limit the maximum differential pressure. Old generation controllers have controls for selecting the required cabin altitude and cabin altitude rate of change. They send signals to the electric motor-driven outflow valves. On modern aircraft, most of the control is done automatically by an electronic controller. The controller receives electrical signals proportional to aircraft altitude and cabin altitude. It will then control the outflow valves to maintain a cabin altitude according to an inbuilt program. On the Boeing 737, the pilot selects the aircraft cruise altitude and landing airfield elevation during his pre-flight preparation. The controller automatically controls the outflow valve to achieve and maintain the appropriate cabin altitude for the phase of flight. On most Airbus types, during normal operation, the pilot makes no inputs to the system at all. The controller receives all necessary altitude data from the flight management computers. This schematic diagram shows the arrangement of the pressurization control system of a modern passenger transport aircraft. The automatic controllers are duplicated and have inputs from the aircraft static pressure sensing system, the cabin pressure sensors, and the air-ground logic system. If pre-pressurization, that is, pressurization on the ground prior to takeoff, is part of the schedule, then inputs are also required from the thrust lever positions. One controller is operating and the other is on standby. The roles are automatically reversed after each landing. In the event of a failure, the standby controller will automatically take over control. The controllers are normally located away from the flight deck in an electrical service center. Each outflow valve is operated by one of three electric motors. There is one motor for each automatic controller and another for manual control. The minimum indications required for a pressurization system are cabin altitude, cabin vertical speed, and cabin differential pressure. This information can either be presented on direct reading gauges or electronically on an LCD screen. The cabin altimeter measures cabin pressure, but it is expressed on the gauge in terms of the equivalent pressure altitude of the cabin. The cabin vertical speed indicator, VSI, indicates the rate at which the aircraft cabin is climbing or descending. The cabin differential pressure gauge indicates the difference between the air pressure inside the cabin and the outside air pressure, and is generally calibrated in pounds per square inch. In the event of a malfunction of the pressure controller or outflow valve, A high pressure reading on this instrument would indicate that the safety valves were controlling the cabin pressure at the structural maximum pressure differential. The cabin pressurization control panel is remote from the pressurization controller and will generally be fitted in the overhead panel on the flight deck. The control panel may have rotary knobs for the pilot to set the expected cruise altitude and the elevation of the landing airport. In a typical system, there are 3 modes of operation: auto, alternate, and manual. In auto mode, one of the 2 automatic pressurization controllers will be operating. The pilot can force the system to use the other controller by selecting alternate. Selection of manual will lock out all normal automatic functions and enable the pilot to control the position of the outflow valves. We will now take a look at a typical flight to see how a typical pressurization system will operate in the auto mode. During his pre-flight preparation, the pilot will set the expected cruise altitude and the landing airfield elevation. In our example, the aircraft will be cruising at 30,000 feet, before landing at an airfield with a pressure altitude of 1,000 feet. With the aircraft on the ground, the operating controller will hold the outflow valve fully open. When the pilot opens the thrust levers for takeoff, the controller will signal the outflow valve to move towards closed, pre-pressurizing the aircraft cabin into a small differential pressure of approximately 0.1 psi. This ensures that the transition to pressurized flight will be gradual and that there will be no surges of pressure on rotation. As the aircraft takes off, the ground air logic system will signal the controller to switch to proportional control. The controller will sense ambient and cabin pressure and position the outflow valves to control the rate of cabin pressure reduction, or cabin climb, in proportion to the rate of climb of the aircraft, so that slightly less than the maximum permitted differential pressure is attained as the aircraft reaches its cruising altitude. The cabin rate of climb will normally be between 300 and 500 feet per minute, with a maximum limit of 500 feet per minute. If the aircraft is required to level off during the climb, then the pressurization controller will sense this and level off the cabin. When the aircraft begins to climb again, the controller will once more position the outflow valves to control the rate of change of cabin altitude, in proportion to the rate of climb of the aircraft. The cabin rate of climb will again normally be between 300 and 500 feet per minute. When cruise altitude is reached, the controller will maintain a constant cabin altitude. There will now be a constant mass flow of air through the cabin. The mass of air coming in from the packs will equal the mass leaving through the outflow valve. Once established in the cruise, small changes in aircraft altitude will be accommodated without any change in cabin pressure. However, if the cruise altitude has to be increased significantly, then the flight altitude selection will have to be reset. If this is not done, and the maximum differential pressure is reached, the controller will not allow further increase in differential pressure, and the aircraft will now be in maximum differential control. As the aircraft climbs, the cabin will also climb, to keep the differential pressure within limits. When the controller senses that the aircraft is descending, it will switch back to proportional control and descend the cabin at a rate to produce a differential pressure of approximately 0.1 psi on touchdown. The descent rate will normally be about 300 feet per minute. When the aircraft lands and the ground air logic system switches to ground mode, the outflow valves will slowly open fully to equalize cabin and ambient pressures. On older types of aircraft, the cabin is not pressurized prior to takeoff. And, because the fuselage is not designed to absorb the landing shock simultaneously with pressure differential forces, the cabin is completely depressurized just prior to landing. With the system under manual control, the outflow valve position can be adjusted by operation of the manual open-close switch. The pilot now controls the differential pressure, cabin altitude, and cabin rate of climb or descent. On the system shown here, a placard along the bottom of the control panel shows cabin altitude against aircraft altitude at maximum differential pressure. The pilot can consult this in order to establish the cabin altitude required for any given aircraft altitude. Opening the outflow valve will cause the differential pressure to decrease, the cabin pressure to decrease, and the cabin altitude to increase. The cabin VSI will show a climb. Closing the outflow valve will cause the differential pressure to increase, the cabin pressure to increase, and the cabin altitude to decrease. The cabin VSI will show a descent. Cabin rates of climb and descent should be carefully monitored and should not normally be allowed to exceed 500 feet per minute during the climb or 300 feet per minute in the descent, in order not to cause too much discomfort for the passengers. That is the end of the lesson. You should now understand the relationship between cabin pressure, cabin altitude, and ambient pressure. Remember, in level flight, if the outflow valve is opening, the cabin vertical speed indicator will show a rate of climb, the cabin altitude will increase, and the differential pressure will decrease. If the cabin altitude reaches 10,000 feet, then an oral and/or visual warning will be given to the crew. Similarly, in level flight, if the outflow valve is closing, the cabin VSI will show a rate of descent, the cabin altitude will decrease, and the differential pressure will increase. If the maximum differential pressure is exceeded, then the positive pressure relief valves will open. Finally, remember that if the pressurization system is in the manual mode, the cabin altitude, the cabin rate of change, and the differential pressure are all controlled by the pilot operating an outflow valve manual open-close switch.